Okay, so this is Unit 4, Video 3, last video of the unit, and it won't be a very long one. But basically we're just going to talk about friction and how that force affects some of the other things that we've been talking about. So when an object is in motion on a surface or through a viscous medium, so honestly it doesn't have to be viscous by any standard, as long as it's in some kind of medium, there will be some resistance to the motion. So friction is really just a resistance to motion. And it's just due to the interactions between the object and the environment. So the resistance to motion is friction. The first type of friction, we have two types of friction. The first type is called static friction, and we note it with we use like a little f for friction, and we use a little s for static friction. So what static friction is basically it resists an object's tendency to start moving. So basically you can only have static friction if you're already at rest. And so basically what it does is it just wants to keep that thing at rest. So it's kind of like when you're trying to move furniture on carpet, and when you first try to move the couch, right, it's really, really hard to get moving. And then once you kind of get it moving, you kind of get over that little hump, then it's a little bit easier to move. And so that first little hump is the static friction. So static friction is always going to be bigger than the other type of friction that we're going to talk about. But this is the biggest kind of friction you're going to have. The most interesting thing about static friction is that there's like a limit of static friction on each item, like, right, depending on the two materials, the two surfaces. So there's like a maximum static friction. And so let's say the maximum static friction on two objects is 50 newtons. So if I push with 20 newtons, the object won't move. If I push with 30 newtons, the object won't move. If I press with 40 newtons, the object won't move, but the static friction will just keep following me. So it'll be 20 if I push 20, it'll be 30 if I push 30, it'll be 40 if I push 40. As soon as I push a little tiny bit over 50, which is its maximum, that's when the object will start to move. So the static friction will just match the force all the way up until its maximum, and then after you surpass the maximum friction, that's when it will start moving. And so you can kind of see this here. So you have, as you increase the force, it's just going to be equal to the static friction all the way up until you hit the static friction's maximum amount. And then that's when it'll start moving. So we usually use this. So the static friction is less than or equal to the coefficient of static friction, which we're going to talk about coefficients of friction in a second, times the normal force. We only use an equal sign if the object is right about to move, if it's just about to move. So we'll talk about the sign later. The sign's really not that important. But basically, if the static friction is bigger than your force that you're pushing against the object, then the static friction is going to win and the object won't move all the way until you hit the maximum. Now, coefficients, and we use this letter, it's the Greek symbol for mu, like a cat, like mew, like a cat. And what it is it's the coefficient of friction. If you have a little s, that means it's the coefficient of static friction. And really what it is each surface or each material is going to have its own coefficient of friction that's just like it's already like its innate state. So like sandpaper is going to have a really high coefficient of friction because it has a lot of friction. It's really like how rough is the surface. Ice is going to have a super, super low coefficient of friction because it doesn't cause a lot of friction. But coefficients of friction and frictional forces are different. Frictional forces are dependent on the coefficient of friction. But the coefficient of friction is not a force. It's just a coefficient. There are no units associated with it. So friction is really made up of the coefficient of friction times the normal force. And you'll see in the next type of friction, it's just going to be the coefficient of that type times the normal force. So let's move on to that. So the second type of friction is called kinetic friction. So kinetic is should remind you of like movement. So you have kinetic friction if you're in motion. There's kinetic friction between two objects if they're in motion or if one of them's in motion on the other one. So we don't see any kinetic friction until you've already overcome the static friction. Now kinetic friction, we use the same little f and then we just use a little k. And basically we just say that kinetic friction is equal to the coefficient of kinetic friction. So objects are going to have one coefficient of kinetic friction and one coefficient of static friction. The static will be bigger times the normal force. So this is your overall equation for kinetic friction. So basically, we're just kind of going to look at this overall. For small applied forces, the magnitude of the force of static friction equals the magnitude of the applied force. So here's a trash can, here's the weight, here's the normal force. As a force is applied, the static friction will just become equal to that force until it breaks through the maximum. As soon as it breaks through the maximum, that's when the thing will be in motion. And so as soon as it's in motion, now the friction is not static anymore, it's kinetic. And it's usually going to be, well, it will be smaller than the normal, not the normal force, I'm sorry. It's going to be smaller than the applied force. And that's because the thing is in motion. If they're equal, then the thing is going to be in constant motion with no acceleration. So we'll go through some of those examples. But the graph is really interesting. So the friction builds up like this. At rest, the object gets a force put on it. As you increase the force, the static friction increases. So increase the force, increase the force, increase the static friction. It just keeps matching the force all the way until we hit the static friction max. And as soon as we hit that, we feel this like little relief as the object starts to move. We feel this like little like whoop, and the friction basically just all of a sudden goes from static to kinetic, and kinetic friction is always lower than static. So it's like moving that couch. As soon as you get past that little hump, this is the hump, then it's kind of easier to move because you're only working against kinetic friction and not static. We'll talk about this more in class. A few more things to know about friction. The friction is proportional to the normal force. So remember, normal force is the force of a surface on an object that basically keeps the object from falling through the surface. So things that weigh more, right, are going to have a higher normal force. And so if you kind of push down, like you could even try this at home, if you push down on a book and try to slide it across the table, it's going to be harder than if you just try to slide it without pushing down on it. So the more you push down on objects onto a surface, the bigger the normal force gets. And then the bigger the normal force, the bigger the frictional force. So I'll show you this example in class. Excuse me. The force of static friction is generally and actually always greater than the force of the kinetic friction. The coefficient depends on the surface. Remember, the coefficient is just like an innate, I don't know, kind of just a thing that all surfaces have. And so it just depends on what the surface is. The direction of the frictional force is always opposite of the motion. And the coefficients of friction are nearly independent of the area. That's not really that important, but the area of contact doesn't really matter. The coefficients are going to stay the same on like a general surface. These are just some of the coefficients of friction. So like steel on steel, you can see that kinetic is less than static, but that's the friction. Aluminum on steel is a little bit less friction. Copper on steel is even less. Rubber on concrete has a lot of friction, especially a lot of static friction. So that's actually really good because we want our tires to not skid on the road, right? When we drive on ice, we have a lot less static friction. And then you can kind of look through these, but that's basically it, right? So ice on ice is going to be really, really low. So you can kind of look through these, but these are just the coefficients, the mu's. So here's an example, and we're going to solve this problem in just a second. But for the block on a ramp, now that you have friction, really nothing changes except for the fact that you would just add a frictional force going against the motion. So friction will just go up the ramp. So in this case, you're going to have normal force going perpendicular to the surface. You're going to have the weight going straight down. Remember, it has components, mg sine theta, mg cosine theta. And then you have your static friction going up. So in this case, static friction is really just fighting the x component, this one here, mg sine theta, is really just fighting the x component of the weight. And then the normal force is fighting the y component of the weight. In problems like this, where they're connected objects, we're also going to do this example. Same exact thing you did before, except for now you're going to have some kind of kinetic friction pulling back this way, and a tension pulling this way. So it just changes it so that this free body diagram has an extra force on it. But that's really all that happens. Some other types of friction, friction between the moving car's wheels and the road is static friction. So basically the car turns like this and it pushes back on the road. If the static friction isn't big enough, then the car will slit. The wheel will kind of skid out. And that's what happens when you're on the ice, is your tires can't grip. And there's not enough static friction for your tires to kind of push back on. And so that's why you skid out. And then air resistance is another type of friction, but we don't really deal with air resistance very often. All right, so let's get to this first example. So it says, suppose a block of mass, 2.5 kilograms. So there's our mass. Remember, kilograms is our mass unit. So I'm going to write down mass equals 2.5 kilograms. Is resting on a ramp, so it's at rest. So that's kind of something to note, just because you'll know what type of friction you have. if the coefficient of static friction, so that's my mu s, between the block and the ramp is 0.35, notice there's no units, what maximum angle can the ramp make with the horizontal before the block starts to slip down? Okay, so let's set this up, and then let me switch you over to the video here. All right, here we go. Focus in. All right, so right now we have a ramp. Let's go ahead and draw our ramp. It doesn't matter which way you draw your ramp, if you want to draw it this way or this way. It doesn't make a difference. I like to draw my ramps this way. So here's my block on my ramp. Here's the angle I'm looking for, right? I'm going to have a normal force. I'm going to have a static friction force. That should be a little f. It doesn't really matter if you use little f or big F, but we'll just stay consistent. And then we're going to have the weight pulling down. So this is the mg. Now, remember, mg has components. It has a y component and it has an x component. And remember, this angle is equal to this angle. So these angles are equal. So I'm assuming that my xy coordinate system looks kind of like this. So it's kind of sideways. So this is directly in the y direction, and this is directly in the x direction. And then I have my mg, this would be mg cos theta, right? And my mg sine theta. My mg cos theta is in the y, and my mg sine theta is in the x. And you could take this vector and you could move it here if you want. So this is also mg sine theta, right? You can kind of move it up there. So you guys can see that. Okay, so they told us it's at rest, this is its mass, this is its coefficient of static friction, and we're trying to figure out what theta, the biggest theta could be, in order to make it so that the block doesn't slide down, I think, right? Is that what it said? So it said maximum angle before the block slides down. So if the block is going to slide down, at that second when it's going to slide down, the forces in this direction are going to have to just be equal, because the only force that's making us fall down the ramp is this little component of weight. This little mg sine theta is the only piece pulling down the ramp. The Fs, the static friction, is what's pulling us up the ramp. So in order to get the block to move, the mg sine theta would have to just equal the static friction right before it moves. It's going to equal the static friction. So I'm going to set that up. I'm going to say mg sine theta would be equal to Fs in our condition, right, for what we want. Now, let's try to plug some stuff in. So I know the mass, it's 2.5. I know gravity's 9.8. I'm going to ignore the fact that it's negative just for right now, because I just need the magnitudes to be equal. And we're just trying to find theta. So we'll ignore the signs just for this moment. Now, the static friction, remember the equation for static friction is mu static coefficient times the normal force. So we know the static friction coefficient is 0.35, and we need the normal force. Now, if we look back at our picture, the normal force is here, and then it's only fighting the y component of the gravity, right? It's fighting this mg cosine theta. It's pulling down. Now, since this box is at equilibrium in the y direction, it's not flying up off the ramp, and it's not going into the ramp, accelerating, right? Since it's just at rest, the normal force is actually going to equal the mg cosine theta. Those two have to be equal. It's like a tug of war. Neither one of them is winning, because this thing is just still sitting on the ramp. So we know that n has to equal basically the opposite, right, of mg cos theta. So n is going to have to be negative, let's see, 2.5 times negative 9.8 cos theta. So if we get rid of this negative signs, n is just the positive version of mg cosine theta. So now let's take that and plug it in. So we have 2.5 times 9.8 sine theta equals 0.35 times 2.5 times 9.8 cosine theta. Now we have one variable, right? One unknown, really. So I'm just going to cancel the 9.8s there on both sides. I'm going to cancel the 2.5 there on both sides. You don't have to do that. You could have done the math, but it's easier this way. So sine theta equals 0.35 cosine theta. So if we divide, we get sine theta over cosine theta equals 0.35. And hopefully trig has been our friend, and we know that this is tangent theta. This is a pretty uncommon type of problem to have this trig in there, but it's worth doing. So I'm just going to do the inverse tangent of 0.35, and I'll get that theta is equal to 19.3 degrees. So 19.3 degrees is the biggest angle we can have, and that's the angle that would be perfect for the block to just start moving. It's actually not going to move quite yet, but anything a little bit bigger than that, it is really because I rounded up. But that's the moment when the thing just starts to move, right before it starts to move. That's the angle we would have to have. Okay, so that's example 1. So let's go ahead and move on to example 2. So example 2 says, I'm going to go ahead and set this up also. Example 2 says a block with mass M1, so M1 equals 4 kilograms, and a ball with mass M2, 7 kilograms, are connected by a light string that passes over a massless, frictionless pulley, as shown in the figure. So I'm going to draw a picture. Here's my box. It's a pulley. And it says the coefficient of kinetic friction, so mu k, between the block and the surface is 0.3. Find the acceleration of the two objects and the tension in the string. And then we're going to check the answer for the acceleration by using, we're actually not going to do that. We're not going to use the system approach. It's pretty useless. So we're just going to do A. So we're going to find acceleration and we're going to find tension. Okay? So let's switch back to the camera. All right, so here's my setup. I have the variables laid out. I have my picture. Hopefully we all remember the first step. Put the steps over here. First step, draw free body diagrams for each object. So I have M1. I have, let's see, I have the normal force pressing up from the surface. I have the weight, which would be M1G. I have tension pulling me this way, and I have kinetic friction pulling me back this way. Okay. For the ball, I have tension pulling me up, and I have M2G pulling me down. There are no side forces. Okay. So this one's going to get a little bit tricky, so I'm going to try to help decide what the signs get a little bit tricky, that's all. So let's write our net force equations. So the net force in the x direction for object 1, so for mass 1. The net force in the x direction is going to be all the forces added up in the x direction. So in the x direction for this one, we have t going to the right, so we'll call that positive t. And then we'll subtract the kinetic friction since it's going to the left. And then remember, that's always the net force is always equal to ma. So that's equal to m1 times a in the x direction. Now, the a is going this way, right? We know we're gonna accelerate to the right because of this weight here. And so ax is going to be positive, so I'm just going to leave this positive. Okay? We'll write one for the y direction just to make sure that we're safe here. So in the y direction, we have normal force pointing up, we have m1g going down, and they're going to be equal to 0 since it's not accelerating in this direction. So if we plug in some stuff, we have n equals m1, which is 4 times 9.8. I had already worked the negative sign in right here. Okay, so I had already worked that negative sign for the g in there, so you don't need to put it in again. So n is equal to 4 times 9.8. Is 39.2 newtons. It's just nice to calculate because I know it's going to come in handy when I get to the kinetic friction. Now let's do the same thing over here. So for mass 2, we have the net force, and in the x direction there are no forces, so there's no use doing that one. So we're just working in the y. So we have t pulling up, right, in the positive direction, and we have m2g. I've already counted in the negative sign for the g in the negative direction. And then remember, this thing is going to fall down. This thing is going to fall down. And so when we put in when we set it equal to ma, we have m2, we need to put negative a in order to account for the fact that the acceleration of this ball is actually going to be negative because it's going down. Otherwise, if you don't do that, the signs will come out really weird. It'll mess up your answer. Okay, so we have this, we've used this equation. Now, we have this, we're looking for a and we're looking for t. So we have two equations with a and t in them. So I'm going to go ahead and rearrange this equation a little bit and just solve the equation for t. So from here, let me see if I can zoom out even more. So from there, I'm going to go t equals m1, which is 4 times a, plus the kinetic friction, which I can actually rewrite this as 4a plus, remember, kinetic friction is mu k, so that's my 0.3, times the normal force, which I know is 39.2. So it's useful that I found that before. So I just used this equation. Okay, for the force of kinetic friction. So that's a nice equation. Now let's do the same thing over here. Let's set this equal to t. So t equals m2, which is 7, and we have that negative a, so I'll just pull the negative sign out to the front, plus m2, which is 7 times 9.8. I'm just going to simplify that. So I have t equals negative 7a plus 68.6. So now we have two equations. They're both equal to t. We know the tension's the same in that rope, in both, right? Because the rope is just one rope. So I can go ahead and set these equations equal to each other. So in the steps, right, we wrote F-net equations, solved equations for t, set equal, and solve for a. Okay? So I'm going to set these equal. So 4a plus, let's do this math, 0.3 times 39.2 is 11.76 equals negative 7a plus 68.6. So let's combine like terms. I'm going to add the 7 here, so I'll get 11a equals, and then I'll do 68.6 minus 11.76. And I get 56.84. Divide by 11. So I get A equals 5.17 meters per second squared. Once we have that, it's really, really easy to find T, because all we do is we plug this back into one of our equations. That one or this one would work, it doesn't matter. So then I go T equals 4 times 5.17 plus, and I know this is 11.6, remember I already solved this. So T is equal to 4 times 5.17 plus 11.76. So T is equal to 32.44 newtons. Remember, tension is a force, so it gets newtons. And that's it. Whoops, I'm sorry. So the really important parts of this are the free body diagrams, these equations, right? The net force equations. And then once you're there, then you're just kind of working the math. That's all we really did. Once we were here, we just worked the math. So you just want to keep in mind your new equation for friction, but it really doesn't change the process of this problem, except for the fact that you just kind of have to do this part now, so that you can plug in for this, right? So it just takes it up a step. So that's it. So go ahead and make sure you take good notes on that. We are going to work on some of this in class. I'll give you guys some examples, and we'll go ahead and do assignment 6 in class next time.